going to talk about projectile motion today. We've kind of been talking about two-dimensional motion a little bit so far with some of our vector problems, where we talk about if we've got a constant velocity this way and another constant velocity this way, then we know that our resultant velocity is going to be somewhere off in the middle, depending on these angles and the velocities that we have or whatnot. We've been adding vectors for a few days now. So we're going to kind of take this to the next level, and we're going to talk about what happens if we've got a cliff and we've got some sort of object that rolls off the cliff with a certain velocity. We want to be able to describe the motion of this object. Well, we hopefully have a pretty good idea about what happens in this case. You know, the object, as soon as it clears the cliff, it keeps moving sideways, but it starts kind of, you know, it goes down because it's being accelerated downward by gravity. Now, for real life, yes, that was 3 reals in a row, velocities left and right on the planet Earth are not constant, and that's because of something called air resistance. You know, no matter how small or sleek your object might be, if it's just a tennis ball or something, the air resistance will still slow your object down as it moves left to right. So basically the difference would be, you know, maybe we'll see something like I have in pink would be what would happen without air resistance, and then something like the white or the yellow would be what it would look like with air resistance. It would just slow us down left and right. For our purposes, though, we're going to ignore air resistance in this course for the most part. If you're ever asked to do something with air resistance, they'll tell you what the deceleration is, or they'll give you some information. You'll be able to figure it out. So, but we're going to ignore air resistance. So I think the best way to approach this is just jump in. Let's just do a problem. Okay, so here's our first problem. It says a ball is moving at 5 meters per second when it rolls off the top of a 150-meter tower. How far away from the base of the tower does the ball land? So let's draw a picture. Step 1 is always draw a picture. So here we go. I'm going to draw my tower. Here's my tower. We only need that much of it. Okay, here's the ground down here. All right. My ball is up here, and it's moving at 5 meters per second horizontally. We know that, 5 meters per second. Now we also know that the height of the tower is 150 meters. And we have a pretty good idea that the ball is going to do something like this and hit the ground over here somewhere. And that's what we want to find. We want to find that distance. So this is just an x displacement, sort of delta x is what we want. Well, this may seem impossible at first, and that's okay. Let's figure it out. What do we know? Let's just start writing stuff down. We know vi, which is 5 meters per second, right? We know delta y, now how far the ball moves up and down. It moves 150 meters up and down. We know acceleration in the x direction, which is negative 9.8 meters per second. And that's about it. Now, let's make a note that this vi is the overall velocity. You know, it's the vector velocity. What we probably need to think about is maybe a vix and a viy. We want to think about the components of that. Now, since this is just the horizontal velocity, we're okay. The vix is just 5 meters per second, and the viy is going to be 0 meters per second. Now, like we talked about earlier, we're going to assume that this x velocity stays constant. It's not going to slow down. There's nothing pushing or pulling on it right now. It's just going to keep going at 5 meters per second, left and right, all the way until it hits the ground. So if that's a constant velocity, we have no acceleration, you know, in a perfect world, we could just say, all right, well, v, what was that? That was weird. V equals delta x over delta t. Alright, and we want delta x, right? So if we just knew, since we know v, which is constant in the x direction, vx in this case, if we knew t, we could figure out how far it went, but we don't know t. But we can figure it out. How can we find out delta t? Well, we happen to know a bunch of information in the y direction. We know the initial velocity in the y direction, which is 0, because it just rolled off the top. We know the displacement in the y direction, and how far it has to fall. And we know the acceleration in the y direction. So if you recall, we've got an equation for this. Delta y equals vit plus 1/2 at squared. Since vi is 0, we can ignore this, so that term drops out. So we can rearrange and solve this for t, so we're going to get delta t, I should have put a delta, whatever, equals the square root of 2 delta y over a. And that's really easy to figure out. So delta t is just the square root of 2 times 150 over, and I'm being sloppy here, not including units. Get over it. We should be pretty good at doing these equations by now. Over negative 9.8. And yes, that should be a negative here, because otherwise I can't take the square root. That is a negative displacement. That matters. So delta t equals what? So that is about 5.532.8 seconds. So we know delta t. It's about 5.5328 seconds. Well, since we know delta t, we can plug it in down here, and we can figure out x. Actually, let's just rearrange that. Delta x equals vx delta t. Well, we know both of those. Vx is 5, because it doesn't have it labeled as initial, but really it's also equal to the final velocity in the x direction, because it's constant. So it's 5 times the time, 5.5328, and that gives us about 27.664 meters. So, having known only the initial velocity of the ball and the height of the tower, we can figure out how far away from the tower the ball is going to land. And that's pretty cool. We could also figure out, if we wanted to, how fast the ball would be moving when it landed, the angle at which the ball hit the ground. We could do lots of different things, but we're going to keep it kind of simple for today. So let's do another. This one says an archer shoots an arrow from a height of 1.5 meters with a velocity of 55 meters per second. He releases the arrow at 17 degrees above the horizontal. At the end of its flight, the arrow strikes the target at a height of 2 meters. How long did the arrow take to get there, and how far from the target was the archer? Well, let's start by drawing a picture. Okay, so we're going to fire our arrow. This is going to be the arrow. And it starts at a height above the ground of 1.5 meters. Okay, we know that later it hits the target over here at a height above the ground of 2.0 meters. Right, what else do we know? We know that it's fired with a velocity of 55 meters per second, at an angle of 17 degrees above the horizontal. So that means we've got a vector, and I probably should have drawn this better, but we've got a 55 meters per second vector that makes a 17-degree angle here. Okay, let's go ahead and write down what we already know. Well, we already know that the acceleration in the y direction is negative 9.8 meters per second squared, right? Because we're on planet Earth, we assume. Okay, we can also figure out delta y. Now, by the way, how long did the arrow take to get there? We're looking for delta t, and we're looking for delta x. But we can figure out delta y, because we start at 1.5 meters above the ground, and we end up at 2.0 meters above the ground. So, well, how can we do this? Well, we're either, what's the change in displacement, the change in x, the change in y, excuse me. Man, well, we start at 1.5, we go to 2, the change in y is 0.5 meters. We end up half a meter higher than we were to start with. Okay, so it looks like if we knew anything else, we could figure out delta t. Well, we do have some other information. We know v. This is just plain old normal v. Our velocity is 55 meters per second. What we need to do is we need to break that up, and we want a vx and we want a vy. How can we do that? Well, our 55 meters per second can be broken up into a horizontal component and a vertical component. We can get vx and vy. And remember that vx is just going to be 55 cosine of theta, which is 17, right, because that's 17. And vy is going to be 55 sine of 17. So we can very quickly and easily get our components. And through the magic of technology, here they are, 52.5967 and 16.0804. Alright, so what now? Well, we've got, let me write these up here. So we know Vx, so we just found it, 52.5967, and we know Vy, 16.0804. Let's move the rest out of the way. Now note two things here. First thing I want to note is that our Vx is constant. This is going to be the Vx at the beginning and at the end, because we assume there's no acceleration. The Vy, however, is really Vyi. It's the initial y velocity. So if we know initial velocity, displacement, and acceleration, we can figure out time. How can we do it? Delta y equals VIT plus 1/2 AT squared. Oh, except that this is very unpleasant to solve for t, right? Because VI is not 0. So we're actually going to need to solve for VF first. So we'll instead say VF squared equals VI squared plus 2A delta y. These are all y's, just to be clear. So solving for VF, y, we're going to have the square root of VIY squared plus 2AY delta y. So let's plug in 16.0804 squared plus 2. This is where signs are really important, because notice that our A is negative 9.8, but then our displacement isn't negative. because we went up. So that's 0.5. So again, through the magic of technology, we get plus or minus about 15.773 meters per second. Now, why did I make the point of saying plus or minus here? Well, because it matters. If it's positive 15, that means the arrow is still moving up. So we got a situation where the arrow was fired, and before gravity could make it arc down, it hit the target. So the target's like right here. Or maybe the target's over here when we hit it, and we're going 15 meters per second down in the y direction. We're going to assume we're over here. So we're going to assume that that our VFY is negative 15.773 meters per second. That's because we're going to assume the arrow took this kind of flight, that it didn't just immediately hit the target right there. If you need more explanation on this, raise your hand and I'll come break it down for you a little further. So we found our final velocity in the y direction. Right, so now that we have VF, we can solve for delta t. We can just use the simplest of all possible ones, and we can say VF equals VI plus AT. So if VF, if we want to solve this for t, what do we get? We get t equals VF minus VI divided by A. Okay, so negative 15.77 minus 16.0804 divided by negative 9.8. So you get delta t is equal to almost exactly 3.25 seconds. Alright, so we've solved this. We're good here. Check. I want to find how far from the target the archer was. So we're looking for delta x. So let's see. Alright, so if we're finding delta x, remember this is a constant velocity, so Vx just equals delta x over delta t. Well, we know delta t, we know Vx, so we can just solve for delta x. Delta x is going to be Vx delta t. Okay, so Vx is 52.5967. T is 3.25. So delta x is going to equal about 170.94 meters. So this isn't really that bad. It's just you really have to break your problem down. You got to do every step. You got to go really slow. You got to think about what's happening. You have to reality check your problem. Be like, okay, is this going to be a positive or negative velocity when the arrow's through flying? You know, I showed you a lot of different things here. So I think I'm going to stop with just these two examples for now. And there's only 5 questions on today's classwork. So I really just want you to jump in, give it a shot. Make sure you're asking lots of questions if you're stuck or you need help, because I think that's how you learn best.